Hello, everyone. This is part two of my lectures for Anne Arundel Community College for Physics 211. We're going to be discussing Chapter 7, which is divided into 4 parts. This is part 1 of 4 and is dealing with potential energy and energy conservation. I refer those in the class to page 1 of their note packets. And here's an example of potential energy in action, or rather potential energy in inaction. This is balancing rock at Arches National Park in Utah, where you have this very large boulder, which is balanced precariously on this sort of outcropping or promontory. This is caused by a differential rate in erosion, so the boulder erodes more slowly than this sort of promontory does. Eventually, this is going to erode away so much that the rock will fall and release all of its potential energy in a spectacular crash. So I suggest that you go out and see this while it is still potential and not kinetic energy. So far, we talked about work, and we've talked briefly about conservative forces. That's in the lecture notes for Chapter 6, the videos of which are posted on the YouTube channel. So far, we've just talked about work and defined the total amount of work as the sum of work done by all forces on an object in the system. But we can split up work into work that is done by conservative forces and work done by non-conservative forces. The importance of this will become fairly clear in a moment. As a brief reminder, conservative forces are the sorts of forces that allow the conversion between kinetic and potential energy. So that's if you have a mouse, for instance. Gravity is doing negative work on this mouse as it's being brought up to a particular height. It is slowing the mouse down as it's being accelerated upwards. However, the work that is done by gravity is stored in a larger amount of potential energy, which can be released when I drop the mouse. And this is a definition of a conservative force. It's a force whose work you can get back out of it in a fairly easy manner. That's either by dropping a ball or something from a great height that you've lifted to that height, or if you are compressing a spring, if you have a block or a mass on a spring, and you have compressed that spring, and then you release the compression, the spring is going to go spring and release the stored energy. That's an example of a conservative force. The work done between 2 points of any conservative force can be expressed in terms of a potential energy function. So in other words, work that is done on that conservative force, or negative work that is done by that conservative force, it corresponds to an increase in potential energy, whereas the reverse is true. A reduction in potential energy is positive work done by that particular force. The work done by a conservative force is fully reversible. So if I compress a spring and then I release the spring, if there's no friction whatsoever, the amount of energy that we get out of releasing the spring is going to be the same amount of energy required to compress that spring in the first place. Conservative forces are also independent of the path between 2 points. So again, if I have this computer mouse and I have it at a particular height, it does not matter how that mouse got to that particular height, whether it was raised in a straight line, whether it was dipsied and doozied and moved all over the place, up, down, and sideways before coming to rest at that particular height. The work done by gravity, and therefore the potential energy of gravity, is dependent only on the displacement from some lower level to some upper level. It doesn't matter how you got there. And finally, the potential energy, the work done between 2 points by any conservative force is 0 if the starting and ending points are the same. So in other words, if I have a mouse at a particular height and I move it up, down, sideways, and bring it back to the same height at which it started, the total amount of work done by the force or on the force is 0. So once again, this is having to do with path independence. And if there is no displacement against that force, then there is going to be no work done either by or on that force. In non-conservative forces, also known as dissipative forces, such as friction, The work done between 2 points of any non-conservative force cannot be expressed in terms of a potential energy function. In other words, friction does not have a potential energy associated with it. What exactly is the potential energy of friction? I mean, what would that even look like? So a non-conservative force is not expressed in terms of a potential energy function. Also, the work done by a non-conservative force is not reversible. Once you have pushed a block across some surface, you have lost energy, or the system has lost energy to heat, and that heat is then dissipated and goes out into the broader universe. Now, you could use the heat of friction to, for instance, boil water, which you could then use to run a steam engine, and you could recover some of the energy of motion of that particular object, but you would not be able to recover 100% of it. You would lose some of it to heat and again to that broader universe. So work done by a non-conservative force is not reversible, and that's what that means. Is essentially there is going to be some loss to the broader universe as heat. The work done by a non-conservative force is also dependent upon the path. So if I'm dragging this mouse across some kind of surface and I'm dragging it in a straight line, the amount of work that is being done as you're dragging it in a straight line is going to be less than if you curve around and you start doing, kind of this serpentine or convoluted path between those 2 points. So there is a path dependence in the work done by a non-conservative force. And finally, if you start and stop in the same place, friction is still doing work. So if you basically drag something in a big old circle, friction is doing work at every single point of that circle as you move it around. So just because your net displacement ends up being 0 doesn't mean that work hasn't been done by friction. So remember, the work done by 2 points by any non-conservative force cannot be expressed in terms of a potential energy function, is not reversible, is path dependent, and is not 0 just because the starting and ending points are the same. So let's talk a little bit about potential energy, and we're talking about things in a conservative force, or in the case of a conservative force. Incidentally, the only 2 conservative forces that we're going to look at in this particular course are gravity and spring forces. Every other force that we discuss in Physics 211 is considered a non-conservative force. So that's in the notes somewhere. I just wanted to emphasize that. Potential energy is the energy associated with a configuration of a system of objects that exert forces on one another. In other words, the position of the object determines its potential energy, not the path, it's just that final position. The amount of gravitational potential energy that an object has is defined by U sub g equals mgy, where m is the mass of the object, g is the constant of gravitational acceleration, or its gravitational acceleration, and y is the y coordinate. And the notes say it says y is a position relative to some reference height that we can choose at our convenience. Remember that you're always going to have further to fall than where you are. If you say, okay, well, our reference height is sea level, then you say, well, what about if I roll a basketball down to the Dead Sea? Gravity is, which is considerably below sea level, gravity is rolling that ball, isn't it? And say, well, and at the bottom of the Dead Sea, you could still drop it down a mine shaft, and so there's still potential energy. So when we're defining potential energy, we are defining some height as y equals 0. And that's basically done in a way that is convenient for us or makes sense. So for instance, if I have a series of ledges, I got one ledge here, and I got one ledge here, and I've got this ball here, and I'm only interested in this ball dropping to this height, then I could say, all right, my reference coordinate is going to be, y is going to be this height here. And I don't necessarily care about any further falling beyond that particular point. So that's what the y coordinate means. It's relative to some reference height that we have set in this particular problem, or whatever problem we're looking at. The amount of elastic potential energy is defined by U sub EL equals 1/2 K, which is the spring constant, times x squared, where x is the position relative to the rest position of the spring. So this is where the spring is neither compressed nor extended nor stretched. The change in potential energy is defined as being equal to the negative of the work done on the object by the force, which is to say that, for instance, the work of gravity is equal to the negative in the change of potential energy. So when gravity is doing negative work, which is when an object is being lifted upwards against the pull of gravity, the potential energy is increasing. And when the potential energy decreases, such as when I let this thing go and I let it drop, then the work being done by gravity is positive. So the work and the potential energy are going to be opposite in sign and equal in magnitude, or rather, more precisely, the work and the change in potential energy are going to be opposite in sign and equal in magnitude. So we're going to talk a little bit about accounting here. I know that that's not necessarily the course that you signed up for, but here we are. The physicist Ernest Rutherford, incidentally, once sniffed that all science is either physics or stamp collecting. And as a biologist and chemist, I kind of take offense at this, and I'll say, well, then all physics is basically accounting. You can be the judge as to who had the better of that exchange, considering that Rutherford won a Nobel Prize, so he would get the last laugh. But he's dead and I'm not, so I have the last laugh. But anyway, a lot of physics is basically accounting. And while you can't account for taste, you can account for a whole lot of other things, and you do in your everyday life. So for instance, just kind of in a general sense, you have some sort of starting amount, you have a change in that starting amount, and that will give you the ending amount, where the change can be either positive or negative. So that's something very simple. If you have, say, 5 cans of Red Bull in your fridge, and you step out for a moment, and you come back, and you find that there were only 3 there when you get back, the change in the amount of cans, or the number of cans, is going to be 2. So 5 plus -2 cans equals 3 cans. What exactly does this have to do with physics? Well, the point is that the cans of Red Bull, or the lack of cans of Red Bull, have to be explained by something. They didn't just magically appear in your fridge, you put them there. They did not just magically disappear from your fridge or get teleported or stolen by aliens. They were likely removed by your roommate. You cannot have magical appearance and disappearance of cans of Red Bull, and as we're going to see, and as I'm going to emphasize repeatedly in this lecture, you can't have energy just sort of appearing and disappearing willy-nilly, and it will. Another example of kind of an accounting problem. If you have a checking account balance in March, and there's some change in the checking account balance, and that will give you the April account balance. And you're really hoping, and I'm really hoping, that this change is a positive number. Similarly, in physics, in kinematics, if you have some projectile or something which is moving at a given velocity, that velocity had to come from somewhere. So in kinematics, we say that the initial velocity plus some acceleration over time is going to give you a final velocity. And as objects at rest tend to remain at rest, and things that most things actually are at rest most of the time, if you're seeing something that's moving at a given velocity, you have to be asking yourself, well, how did it get that way? And the way that you explain that is with acceleration and measuring what that acceleration is. So we also have to account for energy in the universe and in little segments of the universe that we define as systems of interest, or the system that we're treating in any particular case. The total amount of energy in the universe is constant, which is to say that energy can never be created or destroyed. There is a certain amount of energy in the entire universe, And that's all we got. That's all we got to play with for the next, 15 billion years. Of course, you might ask yourself, well, how does the universe have energy at all? And where did that energy come from? That's a better question for your cosmology professor, or depending on what sort of answer you're looking for, your theology professor. But if we're talking about anything outside of the Big Bang, the total amount of energy is constant in the entire universe, which can be represented by saying that the initial energy and the final energy of the entire universe is going to be the same. However, it's difficult to do accounting on all of the energy of the universe, and it's not really practical or interesting to us. We're interested in only looking at little tiny snippets of the universe, which is what we are doing when we define a system. We're saying, okay, we're only interested on this little piece and this little corner of the universe. Let's go ahead and apply a sample system here where we're looking at a soccer ball, which is starting at a height of 6 meters. Let's say that we don't really care how this ball got to a height of 6 meters because we're not treating the ball before it was at a height of 6 meters. But in our universe as we define it, in the system as we define it, the ball is at 6 meters. The ball weighs half a kilogram. And we can calculate how much of each type of energy it has at each point along the way. So for the demonstration, let's not do this on planet Earth. Let's do this on the planet of easy math. And on the planet of easy math, the gravitational acceleration is equal to 10 meters per second squared. We have a handy kinematics equation that we can use here, where v squared equals v naught squared plus 2a sub y times delta y, where y is the change, delta y is the change in the y coordinate. For the sort of free body diagram, if you will, of this ball, I am going to define positive y as being in that direction. All right, so we're going to say that acceleration in this case is positive, and delta y in this case is positive. For k, for the kinetic energy, we know what our formula is for that. It's 1/2 mv squared. And we know that the potential energy of gravity is equal to mgy, again, mass times the acceleration due to gravity times this y coordinate. And the mechanical energy, or the total energy in this system, is equal to k plus u, or the kinetic energy plus the potential energy. The velocity at 6 meters above the ground is 0. We're dropping it from 6 meters above the ground, and it's not actually moving yet at 6 meters. So v squared equals 0. We find that the kinetic energy is 0 joules. So we have 1/2 times 0.5 kilograms times 0, that being the velocity squared, and we find that to be 0. In terms of the potential energy, we have the mass of 1/2 kilogram, the acceleration due to gravity being 10 meters per second squared. Remember, this is on the planet of easy math, and y, in this case, being 6 meters above the ground. Right? And then in terms of the mechanical energy, the total energy in this system is 30 joules, or 0 joules of kinetic energy plus 30 joules of potential energy. At 4 meters, v squared is equal to v naught, and v naught we've already established is 0, plus 2a sub y delta y. Delta y in this case is 2 meters, so that's going from 6 meters to 4 meters, so that is a 2-meter displacement. And acceleration in this case is 10 meters per second squared. So v squared is equal to 40. We just plug and chug. Now, I didn't take the square root of this velocity because we're already wanting to plug in for v squared when we're looking at the kinetic energy. So if we plug in 40 for v squared, we plug in 0.5 kilograms for m, and we have 0.5. We find that the kinetic energy at 4 meters above the ground is 10 joules. The potential energy Once again, we plug in m, g, and y. So that's m, g, and y, and we find it to be 20 joules. And the total energy is 30 joules. Okay? 2-meter case, v squared here is 80. So we have 2 times 10, which is the acceleration due to gravity, times 4, that's the difference between 6 and 2. We leave this in the v squared form, plug into our equation for k, and we find k to be 20 joules, or 0.5 times 0.5 kilograms times 80, which is v squared. Potential energy in this case will be 10 joules, because it's 0.5 kilograms times 10 meters per second squared times 2 being the y-coordinate, the amount that, or the distance that this ball is above the Earth. And the total energy is 30 joules. How about that? And finally, here, v squared is 120. K is 30. U is 0. This is right before it hits the ground. And E is 30. And you'll notice, very conveniently, that these totals are all the same. We're operating here as though this is a closed system, meaning that there is no influence from anything coming from outside the system. There's no wind blowing. There is no friction. There is no drag force, which is acting against this particular ball. It's just the force of gravity. We're neglecting friction. So there's nothing that could take energy away or out of this system. And that means that the energy, the total amount of energy, remains the same throughout all of these different iterations, throughout all of these different positions. So if we're going to draw a little graph, that would look something like this. We see more potential energy here, and then a little bit of kinetic energy. And then here we'd be seeing a little more kinetic energy and a little less potential energy. And these drawings are really not to scale, but these bars, the total of these bars should add up to the same height, and that would be 30 joules in this case. Note that energy can be gained or lost by a system if it is in contact with the outside universe. And this is an important thing to note, is that while the total amount of energy in the universe is going to be constant, the total amount of energy in a system might change. Basically, you can have, for instance, somebody's head might stick in and strike this ball, for instance. That would be a case of the outside universe acting in on this system. If we were to have the force of drag, the force of friction from the air, that would be a case where the outside environment would be taking energy out of the system. However, the amount of energy that flows into the system and that flows out of the system has to be accounted for. You have to ask, about this energy, where did it come from? Where did it go? Where did it come from, Cotton Eye Joe? And I know I just dated myself a little bit there, but I don't mind that too much. Anyhow, you have to be able to know where the energy is coming from and where the energy is going. When it goes into the system, does it remain in the system? If so, you need to adjust accordingly. And if energy is leaving the system, it's left that particular system. So again, remember that energy can flow into or out of a system, but it is not going to flow into or out of the broader universe. All right? How we handle what happens when the ball actually strikes the ground is a topic for another video and another lecture. I believe it's Chapter 8. We'll be looking at elastic and inelastic collisions, which is dealing with exactly this sort of thing, where systems are transferring energy from one system to the other, and this transfer is not always 100% efficient. So understanding what happens when systems collide is an entire other branch of physics that we'll get to before too long. So sneak preview for the next series of lectures. Okay. So let's take an example of energy flowing into or out of the system. Consider a soccer player who heads the half-kilogram ball when it's at a height of 2 meters. And for the purposes of this problem, we are going to argue that the ball is headed in a horizontal line. In other words, it's not headed upwards or downwards. And the speed of the ball then increases from 8.94 meters per second to 12.0 meters per second. The ball still has its 10 joules of potential energy because it's still 2 meters above the surface of the Earth, or the turf, or what we are defining as 0 in this case, and 36 joules of kinetic energy for a total of 46 joules. How exactly did I get this 36 joules of kinetic energy? Well, we look at the kinetic energy formula, which is 1/2 mv squared. We make our substitutions. The substitution that we're making for the velocity is this final velocity, or 12.0 meters per second, which is the final velocity here, and we find that it's 46 joules. So there has been an increase of 16 joules of total energy in this system. On the previous slide, we were looking at this system having only 30 joules of energy total. Now it has 46. So how do we handle this when we're talking about conservation of energy? Well, we can modify our equation slightly for the system, where the initial energy of the system plus the amount of non-conservative work, or work done by a non-conservative force, is equal to the final energy of the system, which can be restated as, if we rearrange this, non-conservative work equals the final energy minus the initial energy. And remember, non-conservative work can be both negative and positive. So the non-conservative work could be acting either to slow down or speed up this particular system that we are looking at. Okay? A way to rewrite this is that the non-conservative work is equal to the amount of kinetic plus the amount it's equal to the amount of kinetic energy in the final state of the system plus the amount of potential energy in the final state of the system minus the amount of kinetic energy in the initial state of the system plus the amount of potential energy in the initial state of the system. What we've done is we've broken up E final into its kinetic and potential energy components, and done the same with E sub I. Now you'll note that the work in this particular equation is only referring to work that is done by a non-conservative force. So what about work that's done by conservative forces? Well, that's already accounted for in any changes in potential energy. In other words, if we say that the total amount of work is equal to the change in kinetic energy, and this is something that we discussed in the previous chapter, we then say that the work has two possible components. It has work from conservative forces and work from non-conservative forces. The work from non-conservative forces is equal to the change in kinetic energy minus the work of conservative forces. And you'll note that this work by conservative forces is going to be opposite in sign to these potential energy terms. Okay, if you have work that is done by conservative forces, that will reduce the potential energy of the system, whereas if you have work done on conservative forces, or alternately negative work of conservative forces, that is accounted for by an increase in the potential energy. So that concludes part one. That concludes kind of the theoretical underpinnings of all of this. In the second part, I'm going to be talking about a bunch of example problems. And in the third part, I'm going to be talking about even more example problems. It's your lucky day. So please be sure to tune in next time to see how these are applied, or these principles are applied to real life problems. Thank you, and I will see you next time.